Many people see power delivery like this. A simple connection from power, for example, a battery or power supply, to a device, for example, a chip or processor or anything else what needs some power. And this is wrong. Why? Because it's not so simple. In this video, we will go through 4 different views how people may see power delivery. And we will talk about what is wrong with them, with these views. So let's start. We already know this super simple view. What do you think is a little bit more complicated view on power delivery? And I will help you with this one word, resistance. If someone knows the basics from electronics, they will know that these wires or PCB tracks will have some resistance. So in the second, more complicated view, the circuit will look like this. And then, for example, if this is a 3.3 volt battery and the resistance of the wires or tracks is, let's say, 1 ohm, then the voltage on our chip can be calculated as battery voltage decreased by the voltage lost on this resistor. To be specific, let's say our chip needs current 1 amp, then based on the Ohm's law, the voltage lost on this resistor is going to be 1 amp multiplied by 1 ohm, and that's 1 volt. So the voltage on our chip is going to be 3.3 volt minus 1 volt, and that equals 2.3 volt. Now, many people may say, in reality, we can ignore this resistance because it's going to be like very, very small. So the voltage will only drop a little bit. And I agree. In many cases, maybe we don't need to worry about this. But in reality, this circuit is actually much more complex. It's not only resistance. Before we move further to this even more complex view, let's stop here for a moment and let's have a closer look at this resistor view. So in this resistor view, what do we need to be careful about? Yeah, I would like to talk about this a little bit. Each chip or circuit has recommended operating voltage and maximum current. Let's say our chip needs maximum current 2 amps and the operating voltage is 3.3 volt plus minus 10%. It means it will work correctly when voltage is between 2.97 up to 3.63 volts. Now, if we would like to be sure that our chip is going to always work, what can be the maximum resistance in this simple circuit? What is the maximum voltage we can lose on this resistor? It's 3.3 volt minus 2.97, that's 0.33 volt. And based on the Ohm's law, for maximum current 2 amp, we can calculate that maximum resistance of the wires or tracks can be 0.33 volt divided by 2 amps, and that is 0.165 ohm. Okay, that's the maximum resistance which we can have here and still be sure the chip is going to work properly. If the resistance is higher, the voltage drop on this resistor is going to be too high, and it will cause that the voltage on the power pins of this chip is going to be below 2.97 volt. Now, I would like to mention 2 more things. First, our current is not going to be always 2 amps. For example, when our chip is a processor doing some calculations and switching some pins, the current will be constantly changing. What does it mean? when current on our chip will be changing, then also the current flowing through this resistor will be changing. Based on the Ohm's law, it means the voltage on this resistor will be changing, and it means also the voltage on the power pin of our chip will be changing. Basically, higher current the chip consumes, lower voltage will be on the pin. Lower current it needs, higher voltage will be on the pin. On our power pin, there will not be a nice stable voltage, but based on the current, the voltage will be changing, and it will create noise on the voltage on our power rail. I just wanted to mention this, okay? The second thing I would like to mention in this simple circuit is that the resistance will be always the same for all the frequencies. So it doesn't matter if our chip will be working at 1 Hz or 100 kHz or 5 GHz, the resistor value will be always the same. And now we are moving to the third view on our power delivery circuit. In reality, this is not going to be only a simple resistor. Do you know how we need to change this? Instead of one resistor, the path between the battery and our chip may look more like this. Some resistors, inductors, and capacitors. Why? What can be, for example, an inductor? A wire. Wires are inductors, or tracks, PCB tracks are inductors. What else? Vias in your PCB will be like small inductors. They will have inductance. Now, maybe you may think like, but these wires or tracks or vias, they must have like very, very small inductance. And yes, that is true. And I believe this is exactly the main reason why many people ignore this view, because they think that these values are very small and they can just ignore them. However, for power delivery, every small inductance will influence how power is delivered to your chip. Only the question is if it's going to be a problem for your chip or not. And it's not only about inductors, it's same for capacitors. On real PCB, there will be, for example, many decoupling capacitors, which you may want to consider. They will be all connected to your power. But also don't forget about capacitance between power planes. Or let's make it a little bit more complicated. Don't forget, real capacitors are not actually only capacitors. They have also some inductance and resistance. So the connection between battery and this chip is going to be full of small circuits built from capacitors, inductors, and resistors. Why is this important? Because suddenly, instead of one simple resistor, here we will have something much more complex, something what is called impedance. And one of the differences between resistor and impedance is that impedance can be different for different frequencies. So suddenly, this simple resistor graph may look like this. Every peak and every dip in this graph is going to be shaped even by the smallest resistance and inductance and capacitance, which will be in the path between the battery and the chip. And now it's not so simple to find out what will be the voltage lost on this impedance, because it will be different for different frequencies and also different for different currents. Or when using different words, there will be different voltage loss for different currents, and there will be different voltage loss for different frequencies. And these two different losses will create a lot of noise on our power rail. I mean, a lot of noise. And if you don't know how exactly this impedance graph looks for your board, how you are going to be sure that the voltage on your chip is going to be always between 2.97 and 3.63 volt? You don't. However, you can measure or simulate this graph. It's called PDN impedance graph. And sometimes it may look like these peaks and dips are very small, but think about it. Do you remember what was the maximum resistance we calculated for our circuit? It was like 0.165 ohm. And the impedance peaks in this PDN graph can easily be 1 or 2 or 10 ohms, but only for specific frequencies. And if the impedance increases from 0.165 ohm, that is our maximum resistance we have and which we calculated, if this impedance increases to 1 ohm, then suddenly the voltage on the power pins of the chip will drop down for this frequency by 1 ohm multiplied by 2 amp current, that equals 2 volts. So it will drop down from 3.3 volt to 1.3 volt at this specific frequency. That is far, far below minimum 2.97, which we need on this chip to, be sure it's going to work properly. In reality, if you don't know this impedance graph for your circuit, you mostly may not even notice there may be a problem, possible problem. However, what if there is suddenly a situation when your circuit starts working exactly at the frequency where this peak is? The noise on your power rail will increase a lot and your chip may stop working properly. I will leave a link in description to a video where you can see a real example how the noise will increase when a microcontroller starts switching I/O pins at this special frequency. Also keep in mind that the square waves or signals with very sharp edges, for example, when your chip is communicating with all the other chips or when it is controlling I/O pins or accessing to memory, these kind of sharp signals, they contain all the kind of frequencies. So to build or design a reliable system, you need to be sure or you need to be able to deliver enough power for all the frequencies your chip needs. Of course, often when you design boards, they just may work even without measuring a PDN graph or simulating. But I wanted to point out this topic because it may help you in future when you will be designing high current boards or optimizing number of decoupling capacitors under a processor or FPGA. By the way, that's not all. There is even a more complex view as you can look at the power delivery. You can look at the path between the battery and the chip as on transmission lines full of magnetic and electric fields, or look at it as moving energy from battery to the chip. But I'm not there yet. I still don't fully understand how I should properly imagine this special view. But once I learn this, I can explain it to you if you will be interested. I really hope you found this video interesting. Please leave your comments. Don't forget, in the description of this video, there will be links to other videos which can help you to understand this topic a little bit more. Also, if you are interested to learn more about hardware design, have a look at online courses on Federal website. You can find there online courses for beginners up to advanced courses about designing boards, but also topics like EMC, KiCad, Altium, and other. When you subscribe to my channel, you will motivate me to keep creating these free videos. And that's everything. Thank you very much for watching and see you next time. Bye.